Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am very happy to have Steve Finkelstein with us today. Hello, Steve.
Hey, Frank, how are you doing?
I am doing awesome on this July 11th, 2024 as we record this. And I'm here in Phoenix, and we are definitely in our summer mode. We will get up into the 115s today, the 40-42C, something along that. And how about you? What's your geolocation, Steve?
I'm in Austin, Texas, where we're not quite that hot, about 95, which is pretty typical, and I think typical is better than normal these days. So we'll take a 95.
But
Pretty dry.
I think it also comes with like 95% humidity or something like that.
No, it's pretty dry today.
Really?
So almost nice outside this morning.
Oh, very good. Awesome. Very cool. Let's see. That's an awesome background picture you have.
That is part of what we're going to be talking about in the article.
Yes, it is. We'll get there in a moment. And so, Steve, what do you like to do for research?
So my research focuses on trying to identify the earliest galaxies to form in the universe and understand how they evolved from those tiny little bits and pieces over 13 billion years ago into our big morphologically complex Milky Way today.
Awesome. Awesome. And that is going to bring us to this very awesome APJ letters. First of all, note it's 32 pages and it's a letter, people. So length is not the primary here. Impact is. And this one's got some impact. So 32 pages is a letter. It is open access. It's the open access era. Go grab a copy for free. The complete CEERS early universe galaxy sample, a surprisingly slow evolution of the space density of bright galaxies with Z between 8.5 and 14.5. And Steve, take us away.
All right, so I'll give you a bit of background. So first, this paper is actually part of an APJ letter focus issue. That's why we were allowed to make it so long. So there's a whole website dedicated to the CEERS program on the APJ letter website. And CEERS is an acronym. It stands for the Cosmic Evolution Early Release Science Survey. It's one of 13 early release science surveys done very early on in the JWST mission.
Cool.
They span all of astronomy, and there are many goals of the CEERS program. But one of the key ones, the key goal, was to sort of push beyond the limits of the Hubble Space Telescope as far how far we could see into the early universe, what's happening in the first 500 million years. That's really the limit we could see with Hubble. That corresponds to a redshift of about 10 or so.
Cool.
The CEERS team has about 150 people. They're not all co-authors on this paper, but many of them are. And so a lot of what we're going to talk about is really due to the hard work of many folks in the collaboration. You can see all their wonderful names right there. It's really my research family, and I really enjoy it.
Very good, very good. Good shout out. Good shout out.
So coming to the title, I had the word surprising. And so if something is surprising, you need to have some expectation for what you're going to see. And what we will eventually get to is how does the abundance of galaxies, so the number of galaxies per unit volume in space, evolve with redshift out to higher redshift.
Okay.
And from Hubble Space Telescope observations and ground-based surveys over the past several decades, it's been pretty well established that from redshift of 4 to redshift 8, that's about 1.5 billion years after the Big Bang to about 0.7 billion years after the Big Bang. If you plotted the evolution in the space density of galaxies, you could sort of fit a log-log plot, but you could fit a straight line. It's what we would call a smooth evolution. Okay. Every little bit of redshift you go towards the earlier universe, the abundance decreases correspondingly. That was in great agreement with simulations, so everybody was happy. When it came to redshift greater than 8, so really pushing Hubble to its limits, redshift 9, redshift 10, there was a lot of disagreement, and this is sort of talked about in the intro here, where some folks found evidence in the data for a continued smooth decline. So you just sort of your trend keeps going out to redshift 9, out to redshift 10, and you really can't go higher than that with Hubble. While other folks found an accelerated decline, so even fewer galaxies than would be expected.
Yes.
And so when it came time to write proposals for JWST, of course, we wanted to solve this problem. Is it an accelerated decline, or is it a continued smooth evolution?
Good.
And just getting to the punchline, what we found here is neither. It's actually a slowing evolution. So the flattens out. Now, I'll give you a big caveat here. This is data from but one survey. It's based on the whole sample is less than 100 galaxies, and at the highest redshifts, it's just a handful. So I would say this is A year ago, we had early hints. We're beyond the early hint phase, but not quite to conclusive evidence. And at the end, we can talk about what data we might need to.
We will cover that, indeed.
Yeah.
Okay.
So that's sort of the backstory for what we're trying to do. I can just briefly summarize what CEERS has done. So CEERS is a coordinated parallel survey. So that means we're using 2 instruments at a time. The sort of basis of CEERS is a NIRCam imaging survey. That's the workhorse imager from JWST. We did a mosaic of about 90 square arc minutes, and you see part of it colorized behind my head right now.
Very cool. I like the live figure. There we go.
And at the same time as that, we took in parallel, or really the NIRCam was in parallel to near-spec spectroscopy. So we have spectra for over 1,000 galaxies, many of which were discovered by the Hubble Space Telescope, but some of them were JWST discovered galaxies that we were able to put slits on. And then we also took data with the MIRI mid-infrared imager, and then we also took spectroscopy with NIRCam. Even though it's primarily an imager, you can actually take spectra.
Wow. Okay. I didn't know
This
that.
paper focuses mostly on the imaging. We're trying to use imaging to identify really early galaxies, really high redshift galaxies. And so the intro just sort of motivates doing all that. This is actually the 3rd paper in a series from the CEERS team. In our very first paper, written in just days after we got some of our data, we reported the discovery of the first redshift greater than 10 galaxy from this data set. It's an object known as Maisie's galaxy, named after my daughter because we found it on her birthday. That galaxy is now confirmed to be at redshift of 11.416.
Wow.
So that's exciting. That object is still features in this paper, but instead of one, it's one of many.
Yeah.
A couple months later, we wrote another paper using about 40% of our data. We hadn't collected all the data just yet. We got about 40% in June of 2022, and the remaining 60% in December of 2022. So the second paper focused on that first 40%. We found, I believe, 26 galaxies at sort of redshift 8.5 to 14. I can't remember what the highest redshift was. So, and this paper was meant to be a very short update to that second paper, now using all of the data to sort of make a more complete sample. As you can see, I'm incapable of writing short papers. I have written one real APJ letter, a 4-page one, but it was many, many, many years ago. So this, what we found was interesting. We ended up going in a lot of cool directions that we'll explore today. So that's why we wrote this paper, trying to use the full CEERS data set now to get a conclusive, at least from this survey, what do we see in the early universe.
Nice. Very nice. Okay.
All right. So going into section 2 of the data, I sort of already summarized what CEERS does. We have 10 pointings with the NIRCam camera, and in each pointing we have observations in 7 filters. There are sort of 6 broad bands spanning 1 to 5 microns, and then we also have 1 medium band at 4.1 microns. We also have some information there on our data releases, and a huge shout out to Mick Bagley, who is a research fellow in my group, research associate in my group, who I saw was also featured on your author.
I was just going to say that.
Another survey we've done called NGDeep. They are one of the true masters of NIRCam data reduction. And so they did the reduction here, and they have created a wonderful website for our program. You can see it there on the left side, ceers.github.io, where not only do we release our data, we have tons of documentation, and we have a data reduction notebook. So you could, if you so choose, download the raw data and reduce it just as we would, and hopefully get to a final data product that looks like what we make.
Very nice. Cool. And we will put a link to Mick's video in the description below this.
Perfect. I'm also drinking out of my CEERS water bottle. I'm very
Yeah,
okay.
you're branded. You're branded.
We're branded. So section 2.1, we won't get into the details. It's all about the data reduction. Suffice it to say, we, and by we, I really mean Mick, has put in a ton of effort. We are going to have a new version of our data dropping soon, sort of our final data release that looks very, very, very nice. It's very clean. We've done a lot about how to deal with this data. Okay. So section 2.2 is all about photometry. So if we want to find high redshift galaxies, we use a technique known as photometric redshifts. And in short, what you do is you take the observed colors of all the galaxies in your images, and you compare them to a set of models of what we think galaxies look like at different redshifts. So you could take a model of like a star-forming galaxy at redshift 0, redshift 1, all the way out to redshift 20, and you could say, okay, let me compare that model to my observations. Where do I get the best match?
Okay.
That's one type of galaxy. There's not just one type of galaxies. There are many types of galaxies, but you can use as many model templates as you want. and you get what we would call a photometric redshift probability distribution function. It's a little curve. Probability is a function of redshift, and we'll see some of this later. To be able to do that, you need accurate photometry. And really you need accurate colors. And so the next, I think it's 3.5 pages of this paper, focuses on the method that we've derived over the past few years with JWST data to produce as accurate colors as possible, to produce accurate uncertainties on those colors, and also accurate estimates of the total flux, how bright something is. You might think that would be trivial, you just kind of count up the pixels, but you can never see all the light, you lose stuff to noise. So there's a lot of modeling that goes into this. That's a whole hour conversation in its own about what we do. But all the details are there, and personally, I'm proud of this part of the paper, even though it's a little bit tedious, because sometimes you only see a few sentences or a paragraph about this process, and the results you get, especially at high redshift, are so incredibly sensitive to some of the choices you make here about how to do photometry. So we try and spell it out in great, maybe too great detail.
No. I love this amount of detail. It makes it easy. If somebody wants to redo it or verify it, it's all here. There's nothing missing here.
Exactly. And when we get to the appendix, there's another little bit there that has to do with reproducibility. Cool. Okay, so let's see. On page 5, we have our first 2 tables. These are giving us the depths that we have for our data. So sort of what is the faintest object you might be able to see. Each row here is one of our 10 near-cam pointings, and then each column is one of our filters. And you can see that from pointing to pointing, there's a little bit of variation, not much. Broadly speaking, we reach roughly 29th magnitude, if we want to put a round number to it.
That's awesome.
And that is a little bit deeper than we thought. You've probably heard before, JWST is performing a bit above specs, which is great. Like that never happens. It wasn't on time or on budget, but it works better than it was supposed to.
Well, there you go.
We'll take that. And you can see we're actually getting a little more sensitive in some of the longer wavelengths, not the 2 reddest ones. You start to drop off a bit. Table 2 shows the same thing for some of the Hubble data. You might say, why are you using Hubble when you have JWST? Well, some of the bands, the 4 wide field camera 3 bands, they are sort of duplicitous with NearCam. We don't really need them. We use them because why not? But the 2 ACS bands, those are optical imaging that is bluer than we get with JWST. So that data is actually fairly important.
Good.
Worth noting here, because not always are these details given, the depths we're showing here are 5 sigma limiting magnitudes measured at 0.2 arcsecond diameter circles and corrected to total. And so this is sort of the true depth. Sometimes folks don't always include the correction to total, and it makes things look a bit better than they are. But this should be an accurate representation of the true depth of the image for a point source, with that caveat implied.
Yes. Cool. Okay. Very good. I'm with you.
All right, section 3, also a long section. How do we actually select our sample of galaxies at high redshift? As I mentioned, I'm not known for my brevity in my writing, but I'll try and be brief here. We basically break it down into sort of 2 categories. The first category is detection significance. So if you scroll down to the next page, on the left-hand side, there's sort of some numbered points. And there's number 1 through 4, that's detection significance criteria. Basically, do we think the source that we found in the image is real? And we do that by placing minimum signal to noise values on that source, because the package we use to do photometry, called Source Extractor, it can find all the real galaxies, but can also find a lot of junk, little noise spikes, hot pixels, other things that are not real. And so these 4 criteria together are designed to minimize the amount of junk we have in our sample. You can often weed those out by eye. We really are working to minimize the amount of by eye things we do. Because again, like you said, reproducibility, we don't want our sample to depend on whether we had our coffee that morning, right? So that's part of it. That's sort of number 1 and number 3 and number 4. Number 2 is a little bit different. High redshift galaxies should not be detected in the bluest filters because they emit no light at those wavelengths, and it's been redshifted all the way out to the near infrared. And so criteria number 2 basically says in certain filters, depending on the redshift, we should not see any light, and so the signal to noise needs to be less than some threshold, which I think we use 2 and 1.5 for some of these.
Got it.
So that's those 4. The next set, photometric redshift criteria. I sort of mentioned a little bit what photometric redshifts or photoz's are. So we use a code called EASY to calculate these. This is a code we've been using in a while. It's easy to use, pun, right? But you can use any templates you want to, and we did some work to devise some additional templates in a previous AppJ paper led by my student Rebecca Larson. So we use those new templates. And then here we say, what are the criteria we use for an object to make our sample? And basically we want a photometric redshift probability distribution that's kind of like a tight Gaussian that has most of its power at high redshift. That's giving you the gist of it. And we'll look at some examples here in a little bit, but you don't want anything that's flat. That means you can't constrain the redshift at all. You don't want anything that has a big peak at high redshift, but also a big peak at redshift 2, because then you're not certain. You don't want to say you can't have any power at low redshift. Otherwise, you basically won't find anything, or you'll find very few objects. They have to be incredibly bright to have 0% chance of being low redshift. So we tried to strike a balance. As we'll show in the very next section, we think we're doing fairly well. So I think that brings us to figure 1, which is about spectroscopic redshifts, which is really exciting because this is not something we could ever do before at these kind of redshifts, because prior to JWST, it was incredibly difficult to get spectroscopic redshifts, even at redshift 6 to 7, let alone 8 to 9. But because JWST works more into the red, you can get really strong rest frame optical emission lines like oxygen 3 out to redshift 9.5. And at even higher redshift, you can actually see this Lyman alpha break, this discontinuity in spectra, where there's no light emitted blueward of it, and then you can sort of see stars redward of it.
Okay.
And so the exciting thing about this paper is because it sort of is kind of wrapping up what we've learned from CEERS, there have been a number of studies that have looked at the CEERS spectra and published redshifts. And so for, I believe, 17 of the sources in our sample, we had spectroscopic redshifts. Okay. Things that are in blue are ones that I called quote unquote good. Things that are in red are ones I called quote unquote bad. And you can see the red sources, the photo Z was kind of 9 to 10 and the spec Z was 7 to 8. So it's not a catastrophe. We're not mistaking, a neighbor to the Milky Way for an early universe galaxy. But they're not in the redshift window we want to study here, which is redshift greater than 8.5. And so we removed those 3 galaxies from our sample, noting that it's not catastrophic, these failures, but we know now they're not in the redshift range, so we're going to take them out.
Yes.
Of the remaining sources, the bulk of them really lie on that 1-to-1 line, that dashed line. So that's good. A few of them have photometric redshifts that are higher. That's okay. It's just an estimate. We could read into the fact that there are sort of more above the line than below the line. Really, with these objects, I think there's 13 blue data points here. It's a little bit hard to make some conclusions. But this is a trend we've seen bear out in other surveys where at high redshifts, photometric redshifts do tend to overestimate by sort of 0.2 to 0.5 in redshift. So not catastrophic. We think it has something to do with the shape of the spectrum near the Lyman alpha break. We think, and we've seen it in spectra, that it's actually shallower than the models assume. And if the models assume a sharp break, that pushes things to higher redshift. So that is mentioned in brief in this paper. But basically what we take away from this plot is our photometric selection, it's not perfect, nothing's perfect, but does pretty darn well.
Pretty good. Gives you a little bit of confidence there. Indeed.
A little bit of confidence, yeah.
Yeah.
Let's see, table 3, the very next table. We actually have 3 tables summarizing our galaxy candidates. Our final sample is, I believe, 88 sources, too big to fit on one page. And so we split them into sources greater than redshift 9.7, that's in this table. Okay. And sources less than redshift 9.7, those are in the appendix. We don't have to go look at it. But
got it.
Down there. Gives you important information like the name we chose to call it, it's a catalog name, their position in the sky, so you can go find it if you want, and then a few magnitudes, some colors, and some redshift information, the photometric redshift, and if we have it, the spectroscopic redshift.
Yes.
All right.
What does NZ mean?
NZ, good question. NZ means it was observed with near spec, but there was no redshift determined. So basically, it was too faint to determine a redshift, which is positive evidence that it's at high redshift, because if it's at low redshift, we should have seen an emission.
Should have got it. Yeah. Okay.
We don't know for sure, but it's probably better. It's probably a good thing, not a bad thing.
Okay. Good.
Okay. A lot of the rest of this section just involves sort of honing our sample. We can briefly talk about figure 2. Although we are looking for the most distant galaxies in sort of an irony of nature, very cool stars or brown dwarfs in our own galaxy can have similar colors to high redshift galaxies. It's kind of crazy. You can mistake some of the nearest things for the far. So we do a check,
Yeah.
and basically the point of this
The
plot
amount.
is our sources are resolved, so they can't be stars. Stars would be unresolved; they'd be point sources.
Mhm.
And the colors of our galaxies are different enough from the expected colors of brown dwarfs. So
Great.
with
Great.
Hubble, where you can only observe out to about 1.6 microns, this is more of a problem.
Hmm.
With GPST NIRCam, you get all the way out to 5 microns. They actually start to look less similar at 2 to 5 microns. So,
Nice. Okay.
maybe we didn't need to have this plot, but we wanted
Uh,
to get as great a confidence in our sample as possible.
exactly. Exactly. And
Okay.
we do want to get rid of those brown dwarfs.
Yeah, so figure 3 is our sort of sample overview figure. And so this is plotting
Eh?
redshift on the horizontal axis and apparent magnitude on the y-axis, so bright on the top, faint on the bottom.
Yep.
And we split our sample into 3 different redshift bins. That's the 3 colors. We're going to make luminosity functions in those bins later. That's why we
Cool.
show it now.
Okay.
And then circles are sources with photometric redshifts. Squares have spectroscopic redshifts. A few other cool sources are highlighted. The red square with a little star in it, that's Maisie's galaxy. Still there, which is great.
No, yeah.
Still there today in our latest reduction. I just looked at it yesterday.
Cool.
And then the very top left point, that really bright one that kind of stands out, perhaps unsurprisingly, has a supermassive black hole at its center that we've seen, that we've also published in this AAS Letter Focus issue and another paper by Rebecca Larson.
Very cool. And how about
Yeah.
the triangles? What do the triangles mean?
Triangles are, I believe, sources with spectroscopic observations, but no confirmation. Yes, that's correct.
Got it. Okay.
Third line caption. Yes, good. Glad I remember.
Good.
And then the background shading is showing our completeness. And so you might wonder, why don't you find anything at redshift less than 8.5? Well, we designed our sample selection criteria to focus on redshift greater than 8.5. And so the fact that it's dark to the left means we are not sensitive there. We could have been if we chose different sample selection criteria.
Right. So
Dark patch on the bottom, though, there we are incomplete because the data is not deep enough to see 30th magnitude sources.
yeah. Okay. Sure. Sure. Okay. So here's our active area. Okay. Good. I'm with you.
All right, next bit of text. We are not the first, this is not the first paper to publish on the CEERS data set. Other folks in the community, as well as CEERS team members, have published on these data. So we do a comparison to those studies. And then finally, figure 4 and 5, which I think are on the next page.
Okay, differences.
It's now showing us some of the actual galaxies for real. So figure 4, we're doing high to low redshift, sort of most exciting to not quite as exciting. So these 3 objects are all of the objects in our redshift 14 galaxy sample, which is, it's kind of crazy to say that because when we wrote the CEERS proposal, we were aiming to really understand the redshift 10 to 11 universe.
Okay.
Yet we have things that we think are at redshift 14, which is exciting.
Nice.
None of these have a spectroscopic redshift, so you can take them with a big old grain of salt. When we talk about the future, I can mention a cycle through program called CEERS, led by my colleague Mark Dickinson, that will observe these sources spectroscopically. So maybe we will get a redshift soon.
Okay.
Going just to the bottom of the page, figure 5, these are now showing sources from our redshift 11 galaxy sample.
Okay.
And we actually chose to show 2 that were spectroscopically confirmed. So the one on the right, that's Maisie's galaxy. We've talked about a few times. That was our first discovery in CEERS. And the one on the left is a galaxy at a redshift of 9.8 that was confirmed in a paper led by Pablo Arbal-Haro, also in this AAS Letter Focus issue.
Nice.
I should explain these plots a little bit because they're all over the paper. And these are figure sets, which was not anything I had known how to do before. But if you go to the electronic version of the journal, you can see all 88 of our sources by clicking through these figure sets without us having to waste paper by putting them in the actual PDF.
Correct. Very good. Figure sets. They're important.
Yeah. So the top row. Oh, sorry. Go ahead.
Go ahead. Let's just walk through the figure a little bit.
Yeah, so the top row of each figure shows little image cutouts. I believe they're 1.5 arc seconds on a side, 1 arc second on a side, centered on the source. And so you can see, usually you don't see it in the left or left few filters. Those are the bluest filters. And then it pops out. That's that Lyman alpha break.
Yeah.
And you can see they're, they're bright. They look like galaxies. They don't look like diffraction spikes. They don't look like hot pixels. They don't look like stars usually. The bottom left plot shows spectral energy distribution. So the blue and green data points are the measured photometry from our catalog.
Good.
And then the blue line is our best fit model from that easy code. And so that best fit model is always at high redshift. That's why it's in our sample.
Very
The
good.
red line shows what if we forced easy to only consider redshifts less than 7. So if we said this
Okay.
galaxy
Okay.
has to be a redshift less than 7, try your best. And that's what that red line is. And then in the right-hand plot, the red and blue curves are the redshift probability distributions for those two scenarios.
Good.
And
Good.
one of our selection criteria actually uses the goodness of fit between these two models as a selection criteria.
Good.
So if a low redshift model is almost as good a fit as a high redshift model, we will toss it out of our sample. Doesn't mean it can't be a high redshift galaxy. We just want it to be somewhat conservative and have a high confidence sample.
There you go.
If it's a significantly worse fit, we used a chi-squared statistic, a difference in chi-squared of greater than 4, then it can make a sample.
Okay, great.
I think in table 3, up a page or two, we have that delta chi-squared value listed. So you can sort of see for every source, everything's greater than 4, and you can see which ones are sort of closer to 4 and which ones are farther.
Take a look at table 3 here real quick. If I get there. Whoop,
It was up above. We passed it before.
oh, sorry. My bad. Okay. Let's just peek at that table 3. This one. Ah, yes. Ah, yes. There's
There we
our,
go. The third
there's
column
our
from the
squares. Uh-huh.
Yep.
Uh-huh. Uh-huh. Okay.
All right, we can jump to page 12. We just have another
Sure.
figure set there.
Sure.
There we go. This is now just showing some galaxies in our redshift 9 galaxy sample. 2 examples here. You can see, sort of similar. They look bright. Now we only don't see them in the bluest filter because they're at slightly lower redshift. But yeah, and these both have spectroscopic redshifts. They happen to be at redshift 8.8 for these two. All these species come from CEERS, with the exception of Maisie's Galaxy. That was actually a director's discretionary time follow-up of a region of the CEERS field.
Okay. Nice. Very good. Beautiful.
All right, let's get into results. So we're ultimately going to measure a luminosity function. And a luminosity function is basically a histogram of galaxy luminosities, how many bright ones are there versus how many faint ones.
Fair.
And we know that it's harder to see faint galaxies. And we know that all of our selection criteria may have kicked out some real galaxies. And so section 4.1 details our attempts to estimate our completeness.
Okay.
So how complete are we to galaxies as a function of magnitude? And we can just look at that figure. That's basically what this figure is showing. The upper right panel shows completeness as a function of galaxy size for different magnitudes. For bright galaxies, we're pretty complete, sort of no matter how big it is. And as you get fainter, you're overall less complete, which means you're detecting fewer of these sources. Okay. And it matters more if they're bigger because their surface brightnesses are lower.
Lower, yes.
Yeah. And so this is all done by source injection simulations where we take little mock galaxies, we add them to the images, and then we try and recover them using our pipeline.
Very good.
And then the plot on the left is kind of what we need for the luminosity function. It shows it's essentially completeness versus magnitude, but we actually fold that completeness into the volume over which we are sensitive to galaxies. And so for bright galaxies, we're sensitive over sort of the largest volume. And as we go to fainter and fainter and fainter, the completeness is lower. And so the volume we would divide by to calculate our luminosity function is lower. That's sort of a completeness corrected volume. It's an interesting way of folding in the completeness that is just the standard in this field. But it sort of gives you a visual sense of, okay, for bright things, we get them all or almost all of them. And as you go fainter, by the time you get to minus 18, you're getting almost none. And so maybe don't trust the luminosity function down there because it's dominated by our completeness correction.
I like this. Very nice. Good.
So we measure the luminosity function. We tabulate it in table 4 on the next page. You can look at it for a second, but then we'll just actually look at the figure. One thing I'll highlight here is the second column gives you the actual number of galaxies in each magnitude bin. Just so you have, few bright things, lots of faint things. That's just something the universe does, whether we're looking at stars, planets, galaxies. The universe likes to make little things.
It does.
Yeah, let's go to, all right, let's go, actually, if we can, we are going to go out of order. Let's skip to figure 9, and then we'll go to figure 8.
Okay. Figure 9, let's do 9, okay.
Because we've been talking about luminosity functions, and these are the luminosity functions.
Woohoo!
So these are the number density of galaxies, so number per unit volume in the universe, per bin, that's what that per magnitude is, versus magnitude. And our data points are those sort of big red circles. There's 3 of them there. This is our redshift 11 bin. The bottom left is our redshift 9 bin, and the bottom right is our redshift 14 bin.
Got it.
we can sort of focus on that bigger one. That's why it's bigger, because I thought it was more important. So a couple points here. The filled red circles, those come from CEERS, this paper. The open red circles also come from this paper, but that's where we're fairly incomplete. And so I show the data, and it's actually pretty consistent with the other data points, but we don't really read too much into those, because there is another survey, the NGDeep survey, which goes much deeper than CEERS. And there was a paper written from NGDeep by Jean Lung, who's a postdoc at UT Austin and second author on this paper, doing the exact same thing in NGDeep, and those are those red squares. And so they are very complete to fainter magnitudes. And so the full luminosity function we consider in this paper are the filled red circles plus the filled red squares, combining these two squares. The little red, faded red data points in the background, those are results from other people, other teams, whether using our data, sometimes using other data. And it's just, there's scatter, because there's a lot of choices you make when you do this, but overall fairly consistent. Our results are consistent with other results. We have our samples larger than many of them, so you can see our uncertainties are smaller in many of the bins. But still, it's always nice to see that you agree. So I think the key thing to take away from this figure comes from those lines. So there's sort of these like gray shaded lines. Those are luminosity functions measured from data at redshift, I believe 5 to 8. This caption is way too long for me to find those numbers, but I think it's 5 to 8. Maybe it's 5 to 9.
Yeah, the gray curve is 5 to 8.
It's 5 to 8. There we go. Using a bunch of data. This was a paper that I wrote with Bagley back in 2022. And so that's how the luminosity function evolves from redshift 5 to 8. The faded red line is if you just continued that smooth evolution, kind of like we talked about in the intro, redshift 11, the faded red line is what you would expect. And what you'll notice is the data is above the line. That's a conclusion that's going to persist for the entire rest of the paper at redshift 11. If we go to redshift 9, it's all the same thing, only now we have a faded blue line. The data are not really above the line, but previous observations existed at redshift 9 that were used in that previous paper I mentioned. So that's not terribly surprising. And then if we go to redshift 14 on the right, now we see the data are significantly above the line. Again, caveat, 3 galaxies in the sample, no spectroscopic redshift. So like exciting, but
caveat in 4.
Don't bet your house on it yet.
Correct.
So this is showing sort of a view of how does the abundance of galaxies we observe compare to empirical expectations. So if we take previous observations and extrapolate to higher redshifts, remember we were talking about smooth evolution. That's kind of what's shown here versus accelerated decline. If we had plotted an accelerated decline, those faded red, blue, and purple curves would be even lower. And what we see is neither, it's above, right? And so this is where the title comes from.
Interesting.
And we'll show that graphically in a bit. But before we get to that, we should also compare to theoretical predictions. And we're gonna do that in 2 different ways. If we go back up to figure 8, just up 1 page. This is a comparison to theoretical model predictions. This is not a luminosity function. This is basically the number of galaxies versus redshift. And it's really number of galaxies at redshift greater than x-axis value. So at redshift greater than 8.5, that's our whole sample. If you go to redshift 10, that's only things at redshift greater than 10. Gray sort of swath there, gray shaded region. That's our results, including a number of sources of uncertainty that you can read all about if you want to, but it includes everything except cosmic variance, which we plot as those separate error bars. And then all the other colored curves are model predictions. And importantly, these are pre-launch models. So these are model predictions based on best understanding of physics before anybody could see any JWST data.
True predictions.
The second we see JWST data, of course, people have all kinds of things they can change to make things. So this is just showing that for the most part, the observations are well in excess of almost all, if not sometimes all, theoretical predictions.
Look at that. All these are all the models. There's your observation.
But if we let's do it out of order again. Let's jump to figure 12, which is on page 19.
You have one remarkable one here. This Beruzzi.
This Beruzzi one, that's an interesting model. It's what we call a semi-empirical model, where basically what that model does is it says that gas, as soon as it falls into the halo, can form stars. So incredibly efficient. So maybe that is in fact what's happening in the early universe, or maybe it's just a happy coincidence.
Could be. We'll find out. Flares is also kind of interesting. That lays within there. Okay, good. Okay, so I'm sorry, where are we going?
Actually, you know what? I was going to go out of order, but let's not. Let's just go to figure 10. We can look at fairly briefly.
Okay. 9, so everything's above. Okay, I'm with you on this one. I'm good, I'm with you. Okay, figure 10.
There we go.
Mm-hmm.
This is now just plotting all three luminosity functions on top of each other.
Yes.
We fit a double power law form to the luminosity function. We don't do a whole lot with that fit. We just do it. We show it in the plot and show it in the table above. But I think
DPL is a double power law. Gotcha.
let's move on to the next figure, which is, I think, one of the key figures of this paper, especially the left panel.
Money shot. Okay.
So in this key figure, on the left-hand panel, we show, again, sort of a volume density of galaxies, but here we're looking at a specific magnitude bin of minus 20.
Yes.
And the red circles show results from CEERS.
Yes.
The blue curve shows those, that actually comes from those gray luminosity function in the previous plot from the paper that Nick Bagley and I wrote. Okay. So the dark blue shows what is observed at redshift 3 to 9. So this is, what we think the universe has done when we've observed it. And then if you just extrapolate that to higher redshift, that's the light blue. And then you can see at redshift 9, our results agree with those that previous paper, which again is kind of by construction because that paper used redshift 9.
Yeah.
As we go to higher redshift, we are in excess.
Yes, definitely.
The evolution of the abundance of galaxies, rather than proceeding at the same rate or declining, is actually slowing.
Going down.
This plot is what the title of the paper is about.
Wow.
Evolution of galaxies is slowing. We quantify it. We give a slope. That's what's sort of inset in the figure. Yeah. We give a significance somewhere. It's 2.1 sigma significance, this sort of excess. So I would say, what do I want to say?
Interesting.
It's not sell your kids or bet your house, but it's, I don't know, bet your favorite appliance, maybe? I don't know. I was trying to think. Bet your favorite appliance, we'll say that.
I'll put
the
my
right-hand plot, I don't want to read too much into, but that is sort of looking at the same thing, but for fainter galaxies. And we see less of a discrepancy there. And so that's very tenuous. We definitely see that bright galaxies are evolving more slowly, the abundance. It might be that faint galaxies don't show this discrepancy, but again, CEERS is not really designed to go super faint. And so I think that still remains to be
big one.
seen.
Mm-hmm.
Yeah.
Very cool. Very cool. Yeah.
And so the discussion of the paper is basically all about why. Why would the abundance of galaxies be slow?
Slow down. Yeah.
So we go through a number of scenarios. So in section 5.1, we talk about redshifts. What if all the redshifts were wrong? We don't think that's the case. I go into this in great detail, but we already showed that the redshifts for many sources were good. And I think we will know more in the near future.
We'll come to that.
Section 5.2 says, what if some of the light in these galaxies came from an active galactic nucleus or an accreting supermassive black hole and not stars? I would say in galaxy evolution, there's sort of two major discoveries that GWST has done. One, more bright galaxies at high redshift than expected. And two, lots of growing supermassive black holes at high redshift. Most of those have been discovered by their red light emission, which implies they're obscured. And here in this paper, we're looking at rest-frame UV light. And so I don't know that that's the answer. In this section, we talk about observation sort of for or against. And so I think what you really need is lots of deep spectra for every source to assess what is actually doing the ionization. That's kind of what you need.
Okay, we'll come back to that point.
Yeah, and section 5.3 talks about a number of changes in physical processes. So if you actually if stars were just different, how could they be different? Okay. One change could be a significant evolution in attenuation, so dust attenuation. Maybe after you cross redshift 9, everything is dust free, like all of a sudden. This has been talked about in some theory papers. Figure 13 is my attempt to show that I don't think this is the answer. Basically, what figure 13 is showing is that galaxies at redshift 8 to 9 were already pretty blue. And so we don't see a huge change in color from 8 to 9 to 11. Like all the dust sort of falling apart.
Fair enough.
So there's a lot of scatter there. I think there's a lot more observational work that can be done there. But we sort of disfavor that. Another scenario we talk about is what if the initial mass function is different?
Yes.
We know that at some point in the early universe, presumably we'll find an era where there's no metals in stars. Those stars are expected to be really massive and hot. that would change the mass to light ratios of the galaxies.
Yes.
Maybe these things contain those stars, and that's why they're so bright. They're easier to see.
Okay.
We don't know if that's the case. We sort of go through some scenarios where if it was the case, it could sort of match what we observed, but that's very speculative.
Okay, sure. Understood.
And then the final part, section 5.4, talks about star formation efficiency. So the Milky Way is like notoriously a bad star former. It doesn't turn very much of its gas into stars. What if high redshift galaxies were better?
Yep.
There's a lot of reasons to think that might be the case, specifically because at this time, the universe was much smaller, much denser than it was today. And so the gas clouds in these high redshift galaxies are also denser than gas clouds today. And theoretical simulations predict that more dense gas clouds will have a higher efficiency of star formation.
Indeed.
And so that's more or less what this paragraph talks about. Higher star formation efficiency might also result in more stochastic or bursty star formation. So we talk about
possible.
And this is all summarized in figure 12, where we show, focusing on redshift 11, we're showing our luminosity function again as the red data points. And now we're showing a bunch of different models. These are mostly post-launch models that have different sort of methods of reconciling data with observations. And you can see now many of these lines agree. So I should see the gray faded lines. Those are pre-launch models. They're below the data.
Yes.
And then many of these lines are now consistent with the data. So all of those scenarios we talk about are plausible.
Yeah.
So
they're all investigating different ones. Yeah.
To conclude, how would you distinguish between these spectra? With the photometry, we can identify the galaxy, we can measure its UV luminosity, we can estimate its redshift. With a spectrum, you can measure metallicities, you can get detailed information on what is doing the ionization. Is it stars? Is it AGN? You could estimate star formation histories. Are these things bursty? You can measure more robust stellar masses, all of these things. And so the hope is that over the next few years, many more programs will be approved that can get this kind of data to actually, answer these questions, which, we say there are a lot of plausible explanations. They're all plausible. They're all exciting. Which one is it? Probably it's some combination of them, but we really need more data.
Very cool. Very, very cool.
I can talk 30 seconds about the appendix. The appendix includes a few tables. The lower redshift 8.5 to 9.5, that's tables 6 and 7 that we didn't want to include in the main thing.
Right.
And then appendix B, this was all about reproducibility. These are sources that we had to remove by eye. Sources that were selected through our automated process. But I didn't want people to worry that it was subjective, or if it was subjective, I wanted them to be able to see it. And so these are just showing in different categories, diffraction spikes. That's the first
edges.
one. The second one is bad pixels. The third one is chip edges. The fourth one is what we call an oversplit region. So there's like a big bright galaxy and the photometry package just sort of latched onto an edge of it and said, this is a galaxy. So we list all those there. In our next work, this list will be much smaller because we've tried to make some improvements on automating the identification of these sources.
Right. But it's good that you, A, admit it's visual, and B, put it in. So I think that's wonderful.
Yeah.
So
and that's
may you never write a small paper again. Steve, I want to thank you so much for walking us through this really nice article. APJ letter, a nice long one. Very cool. Very cool.
Yeah, thank you.
Congratulations to the team as well. So you mentioned it a couple of times as we were going through. So I just want to push a little bit on where do you think we go most immediate and maybe long-term on answering some of these questions. One is spectra, and so on. And so just sort of next steps, where do we go given the published article?
Yeah, so I think sort of two directions. One, as I harped on repeatedly, spectra. So there is this this program called CEERS. It's the Candles Area Prism Epoch Ionization Survey, PI'd by Mark Dickinson. That will be getting spectra for 10,000 galaxies with JWST near specs prism mode over the CEERS field and also 2 other fields from the survey called Primer. It will do a lot for measuring redshifts. It will do some for measuring things like metallicity. The prism has a very low resolution, so you're not sensitive to weak lines.
Got it. Yeah.
So we need deeper observations, and there's ideas. I won't go too in depth because all proposal review is dual anonymous now, but we have ideas for the upcoming Cycle 4 deadline about how to how to try to answer some of these questions.
Cool.
And then the other direction is increasing the sample size, reducing the error bars on this paper. So CEERS doesn't exist in a vacuum. There's a number of other imaging surveys. There's the primer one that I mentioned. There's GTO programs like JADES. There's our own NGDeep survey, the deep field. There's Uncover, all kinds of surveys, and we really need to start combining these data sets to improve the statistics.
So is the CEERS project over? Is this like the final CEERS paper or the main one?
Oh, it's not final, but we got our last data in March of last year. And so data acquisition is complete. We will be doing our final data release very soon.
Okay.
Something of great embarrassment to me is the survey paper is not out yet because I've been writing these science papers instead of writing the survey paper, but that is almost done. And that will sort of be a bookend in this focus issue, hopefully in the next month or two.
Very cool. Very cool. Well, I really look forward to seeing this develop over the next year or two as these surveys and other things come out. It'll be very exciting to see how this goes. So very nice. Steve, thank you so much once again. Appreciate it.
Yeah, thank you. Pleasure to be here.
And I hope this made your astronomy day just a little bit better, and we will see you on the next one. Bye-bye.